Welcome to this presentation on automorphic numbers using Java. In this session, we will learn how to check whether a given number is automorphic using a Java program. This program uses user-defined functions to break the logic into smaller parts, such as extracting digits and counting them. This approach improves readability, reusability, and modularity of the code. In this problem, we are asked to determine whether a number is automorphic. An automorphic number is a number whose square ends with the same digits as the number itself. Let's look at a few examples to understand this. Take the number 5. The square of 5 is 25, and it ends in 5, the original number, so 5 is automorphic. Now consider 25. Its square is 625, which ends in 25. Again, it is automorphic. Let's try 6. The square of 6 is 36. Since 6 has one digit, we only check the last digit of 36, which is also 6, so 6 is automorphic too. But if we try 7, the square is 49, and it does not end in 7, so 7 is not automorphic. In this program, we will accept a number from the user, calculate its square, extract as many digits from the end of the square as the number has. Then compare this portion with the original number. If the two match, it is an automorphic number. Otherwise, it is not. This helps us apply logic, squaring, digit counting, and modular arithmetic in Java using user-defined functions. Let's go through the algorithm step by step. First, start the program and accept a number. Then, count the digits in the number and find its square. Next, extract the last n digits of the square, where n is the number of digits in the input number. If this matches the original number, it is automorphic. Display the result and end the program. In this slide, we'll focus on the extract last digits function, the core logic that helps determine whether a number is automorphic. Let's break it down step by step. This function accepts an integer num as input. Its job is to return the last n digits of the square of that number, where n is the number of digits in the original number. Why? Because that's how we check if the number matches the ending part of its square. So, how does it work? First, it calls another helper function called countDigitsNum to determine how many digits the number has. For example, if num is 76, it has 2 digits. Then, the function calculates the square of the number using num times num. So for 76, the square is 5776. Now comes the clever part. To extract the last n digits, we calculate 10 to the power of n. In our example, that's 10 squared equals 100. Then we use the modulus operator, which gives us the remainder when the square is divided by 100. So, 5776 modulo 100 equals 76. This 76 is then returned. It represents the last 2 digits of 5776, and since it matches the original number, we can say that 76 is automorphic. To summarize, the function uses digit count and modulus to isolate the ending portion of the square. It works for any number of digits, from single-digit numbers like 5 or 6, to larger ones like 625 or 9376. This modular design also makes the program easier to read and maintain. Overall, this function plays a critical role in isolating the logic for checking automorphic numbers by using basic math operations in a reusable way. In this slide, we focus on the countDigits function, a small but essential part of the automorphic number program. The purpose of this function is to count how many digits are present in a given number. This count is used in the extract last digits function to decide how many digits to extract from the square. Let's walk through how it works. The function takes an integer n as input and initializes a counter variable, count, to 0. Then, it enters a while loop that continues as long as n is greater than 0. Inside the loop, two things happen. The count variable is incremented by 1. This keeps track of how many times we loop. The number n is divided by 10 using integer division. This removes the last digit of the number each time. This process continues until n becomes 0. At that point, count holds the total number of digits the original number had. Let's take an example. If n is 625. First loop a, n equals 625, count becomes 1, n becomes 62. Second loop, n equals 62, count becomes 2, n becomes 6. Third loop, n equals 6, count becomes 3, n becomes 0. The loop ends and the function returns 3, because 625 has 3 digits. This function is important because it lets us dynamically determine how many digits are in the number, no matter how long it is. That makes our program flexible and adaptable to any input. Using a separate function for digit counting also follows good programming practice, keeping logic modular, reusable, and easy to test. In this slide, we are looking at the main method, the heart of the program where the execution starts. Let's walk through the steps in this method line by line. First, we create a scanner object named SC to allow user input from the keyboard. Then, we display a prompt, enter a number, and use sc.nextIn to capture the number entered by the user. This number is stored in the variable number. Next, we pass this number to the user-defined function extract last digit's number. This function calculates the square of the number, extracts the last in digits, where n is the number of digits in the original number, and returns those digits to the result variable. Then comes the most important part, the comparison. We check if result is equal to number. If it is, the number is automorphic, and we print a message saying so. If it's not, we print that the number is not automorphic. Finally, we close the scanner object with sc.close to free up system resources, a good practice in Java. Let's take an example. If the user enters 25, the square is 625. The last two digits of 625 are 25. Since this matches the original number, the output will be 25 is an automorphic number. This main method acts as a controller. It gets the input, processes the logic through user-defined functions, and produces the output. It demonstrates good programming practice by delegating specific tasks to functions, making the program cleaner, modular, and easier to debug or enhance later. In this slide you will get the full program link which you can execute the entire program. Also, program link is available in the description box. Here is the variable description table. It lists each variable used in the program, their data types, and what they store or do. This helps us understand the logic and purpose of each component in the program. Here are two sample outputs. When the user enters 76, the program correctly identifies it as an automorphic number. When the user enters 7, it reports that the number is not automorphic. To recap, an automorphic number is one whose square ends in the number itself. We used functions, conditionals, and modular arithmetic in Java to implement this. This is a great example to practice Java logic and function calls. Thanks for watching. Documentation containing question, algorithm, Java program, variable description table, VDT, sample output is also available in description box of this video. Don't forget to subscribe if you are using this for your school or college projects. Happy learning!